This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're delving into a paper detailing the flight validation of a learning-based trajectory optimization system for the Astrobee free-fly robot on the ISS. This is a significant advancement in space robotics, leveraging machine learning to accelerate onboard trajectory optimization. Let's start with the core problem addressed in this research. What were the primary limitations of traditional trajectory optimization methods in space applications that motivated this work?
The primary limitation is the high computational demand of traditional trajectory optimization algorithms. Onboard flight computers in space missions often lack the processing power to handle the complex calculations required for real-time trajectory optimization, especially in dynamic environments. This restricts the autonomy and responsiveness of space robots. The paper addresses this by exploring the use of machine learning to significantly reduce the computational burden.
The paper mentions using a neural network to provide warm starts for the GUSTO sequential convex programming framework. Can you elaborate on the mechanics of this approach and why it's effective?
The approach uses a two-stage process. First, offline training data is generated using a simulator and the GUSTO algorithm. This data maps problem parameters, start and goal points, obstacles, etc. to optimal trajectories. A neural network is then trained on this data to learn this mapping. Online, this trained network takes new problem parameters as input and predicts a high-quality initial trajectory, warm start, for GUSTO. This warm start significantly reduces the number of iterations GUSTO needs to converge to an optimal solution, drastically cutting down computation time.
The paper highlights the use of GUSTO, a sequential convex programming algorithm. Why was GUSTO chosen, and what are its key advantages in this context?
GUSTO was chosen because it offers theoretical guarantees on solution quality and feasibility, crucial for safety-critical space applications. Sequential convex programming breaks down a complex, non-convex problem into a sequence of convex subproblems, which are easier to solve. GUSTO provides guarantees that the solutions of these subproblems converge to a locally optimal solution of the original problem, ensuring a level of robustness and reliability essential for space operations.
The paper mentions both cold starts and warm starts. Can you clarify the difference and the impact on performance?
A cold start begins the optimization process with a naive initial guess, often a straight line between start and goal. A warm start, provided by the neural network, uses a much better initial guess, closer to the optimal solution. This significantly reduces the number of iterations required for convergence, as demonstrated by the results showing a 50–60% reduction in iterations for complex scenarios with obstacles or rotational dynamics.
The results show varying degrees of improvement depending on the complexity of the scenario. Can you elaborate on the situations where the warm start provided the most significant benefit and where its advantage was less pronounced?
The warm start provided the most significant speedup in complex scenarios involving rotational dynamics and obstacles within the training distribution of the neural network. In simpler scenarios, like pure translation without obstacles, the cold start was already quite efficient, so the warm start offered less of an advantage. The benefit also diminished when dealing with out-of-distribution, OD obstacles, highlighting a limitation of the current model's generalization capabilities.
What are some of the limitations of the current approach, and what are potential avenues for future research to address these limitations?
A key limitation is the performance with OD obstacles. Future work could explore more expressive neural network architectures, such as transformers, to improve generalization. Incorporating OD detection mechanisms into the planner would also enhance robustness. Further research could also focus on handling more complex dynamics and expanding the range of tasks the system can perform.
The paper mentions the use of C++, OSQP, and libtorch. Can you comment on the choice of these technologies and their roles in the implementation?
C++ was chosen for its performance and suitability for real-time embedded systems. OSQP, operator splitting solver for quadratic programs, is a highly efficient solver for the convex subproblems within GUSTO. libtorch, PyTorch's C++ library, provides the necessary tools for deploying and using the trained neural network onboard the Astrobee. The combination of these technologies allows for a high-performance, real-time implementation on a resource-constrained platform.
The paper states this is the first demonstration of learning-based control on the ISS. What are the broader implications of this achievement for the future of space robotics?
This achievement demonstrates the feasibility and potential of using machine learning to enhance the autonomy and capabilities of space robots. It paves the way for more sophisticated, adaptable, and efficient robotic systems for future space missions, enabling more complex tasks and operations in challenging environments. The reduced computational demands allow for faster decision-making and more responsive control, crucial for tasks requiring real-time adaptation.
The paper mentions the use of a simulator for training data generation. How accurate was the simulator, and how did any discrepancies between the simulator and the real-world environment affect the performance of the system?
The accuracy of the simulator is crucial. While the paper doesn't explicitly quantify the simulator's accuracy, the success of the flight experiments suggests a reasonable level of fidelity. Discrepancies between the simulator and the real world could lead to performance degradation, especially with OOD scenarios. Robustness to these discrepancies is an important area for future research, potentially involving techniques like domain adaptation or reinforcement learning from real-world data.
The paper focuses on trajectory optimization. Could this approach be extended to other aspects of space robotics controls, such as motion planning or task execution?
Absolutely. The core concept of using learned warm starts to accelerate optimization is applicable to a wide range of control problems in space robotics. It could be extended to other aspects like motion planning, where finding collision-free paths can be computationally intensive. It could also be integrated into higher-level task planning and execution systems, improving overall efficiency and responsiveness.
The paper mentions the use of cubic splines to represent the predicted trajectories. Why were cubic splines chosen, and what are their advantages in this context?
Cubic splines are a good choice for representing trajectories because they offer a balance between smoothness and flexibility. They are smooth and continuous, which is important for generating physically realistic and dynamically feasible trajectories. They're also relatively easy to compute and manipulate, making them suitable for real-time applications. The use of splines allows for a compact representation of the trajectory, reducing the computational burden on the onboard system.
The paper shows a comparison of optimal cost for cold and warm starts. In what scenarios did the warm start result in a higher optimal cost, and why did this occur?
The warm start resulted in a slightly higher optimal cost, primarily in scenarios with out-of-distribution OD obstacles. This is because the neural network, trained on a specific distribution of obstacles, may not generalize well to unseen obstacles. The initial trajectory provided by the warm start might lead the optimizer to a local optimum that is slightly suboptimal compared to the solution found by a cold start, which explores a wider range of the solution space.
The paper concludes by highlighting the potential and limitations of learn warm starts. What are the next steps in this research to further improve the robustness and applicability of this approach?
The next steps involved addressing the limitations of the current approach, particularly the generalization to OD scenarios. This could involve exploring more advanced neural network architectures, such as transformers, which have shown promise in handling complex, long-range dependencies. Improving the robustness to noise and uncertainties in the real-world environment is also crucial. This could involve incorporating techniques like robot optimization or reinforcement learning.
The paper mentions several supporting partners. Can you elaborate on the collaborative effort involved in this research and the roles of the different organizations?
This research was a collaborative effort involving NASA Ames Research Center, ASTROB Group, NASA Johnson Space Center, ISS program, and the NASA Space Technology Mission Directorate. NASA Ames provided the ASTROB platform and expertise in space robotics. NASA Johnson managed the ISS operations and integration of the ASTROB system. The Space Technology Mission Directorate provided funding and support for the research. This collaborative effort highlights the importance of interdisciplinary collaboration in advancing space exploration technologies.
The paper references several other publications. Can you briefly discuss the relevance of these references to the current work?
The references provide context and build upon existing research in trajectory, optimization, machine learning, and space robotics. References 3, 6, 5 describe the GUSTO algorithm and the learning-based warm starting framework. References 213 discuss the broader context of amortized optimization and learning-based warm starting techniques. References 7-10 highlight the use of transformers in related aerospace applications. References 8 describes the ASTROB platform, and 1.12.14 detail the software and tools used in the implementation.
The paper emphasizes the importance of theoretical guarantees in safety-critical applications. How does GUSTO ensure these guarantees, and how does the integration of the neural network affect these guarantees?
GUSTO provides theoretical guarantees through its sequential convex programming approach. By solving a sequence of convex subproblems, it ensures that the solution converges to a local optimum of the original non-convex problem. The integration of the neural network doesn't directly affect these guarantees, as GUSTO still performs the optimization with its inherent guarantees. However, the quality of the warm start provided by the neural network influences the efficiency of the optimization process, potentially leading to faster convergence to a local optimum without compromising the theoretical guarantees of GUSTO.
The paper mentions the use of a feed-forward neural network with a single hidden layer. Why was this specific architecture chosen, and what are the trade-offs involved in selecting a simpler versus a more complex architecture?
A simple feed-forward network with a single hidden layer was chosen as a starting point for its balance between expressiveness and computational efficiency. Simpler architectures are easier to train, require less data, and are less prone to overfitting. However, they may have limited capacity to capture complex relationships in the data. More complex architectures could potentially improve accuracy, but at the cost of increased computational complexity and the risk of overfitting, especially with limited training data. The choice of architecture involved a trade-off between accuracy, computational cost, and robustness.
The experimental session on February 13, 2025, involved a specific set of experiments. Can you describe the types of maneuvers performed by Astrobee during these experiments?
The experiments involved a range of maneuvers designed to test the performance of the learning-based trajectory optimization system under different conditions. These likely included simple translations, translations with rotations, and maneuvers involving obstacle avoidance. The specific details of the maneuvers are not explicitly provided in the abstract or introduction, but the results suggest a diverse set of scenarios to thoroughly evaluate the system's capabilities.
The paper mentions the use of virtual obstacles. How were these virtual obstacles defined and incorporated into the optimization problem?
Virtual obstacles were likely defined as regions in the workspace that the Astrobee robot was constrained to avoid. These constraints were incorporated into the optimization problem, equation 1, as inequality constraints, FBI XTI0, STIA0, limiting the robot's position and/or velocity within these regions. The specific mathematical representation of these constraints would depend on the chosen obstacle representation, dots, spheres, polygons, and the chosen distance metric.
This has been a very insightful discussion on the innovative work presented in this paper. Thank you.